welcome to the lecture of this finite volume method. Now, when you talk about these properties, one of the important another property is transportiveness. So, this is associated with that you can see an image how the let us say a fluid particle which moves along this particular line. It is at location C, okay, and it move along this circle. Some point of time it come W, some point of time it comes to east. So, this has to do with your, so this is a fluid particle, how it moves along that path, okay, and that is sort of defined with the number called the Peclet number, which is the convection strength to the diffusion strength. So, essentially rho u divided by gamma by delta x. Okay. So, this is very important number, that let us say you have a constant phi at C, okay, in the flow field with uniform velocity and diffusivity. Okay. So, you have a fluid particle which has some uniform velocity and diffusivity within the flow field. So, the shape of this scalar field, so essentially this is the shape of this scalar field. The shape of this scalar field actually at some phi will be influenced by these two ratio. Okay. Now, for example, let us say if your Peclet number, so this dotted line actually refers to the shape of this scalar field for some value of phi, or rather contour. You can think about the contour of phi. Now, the fluid particle having some uniform velocity and diffusivity. Now, if the Peclet number is 0, what that indicates? It indicates the transport of phi is governed by diffusion. Okay. So, that means which will have an elliptical behavior. So, which will be a elliptical behavior. Now, in this case, the phi is surrounded by these two location. So, it will have some elliptical behavior, and the iso line, this is the iso line of phi for Peclet number 0, and they are influenced by the neighboring elements at E n. Now, if you increase the Peclet number, okay, if you increase the Peclet number, so essentially this is the fluid particle which are having some uniform velocity and diffusivity. Now, the motion of this fluid particle, which will actually be represented with some isocontour of phi. Now, they are governed by these two ratio. which is given a number, Peclet number between the convection and the diffusion. If Peclet number is 0, then primarily it is governed by diffusion. So, the isocontour will move along the circle and the point at C will be influenced by the neighboring point ahead of it and downstream of it. Now, if I increase the Peclet number, that means my convection is going to now slowly dominate over diffusion. So, the circular shape will become elliptical shape. So, this is the case when Peclet number increases and the phi will be shifted. So, this is how your solution of the fluid particles, they are controlled by the different transportive properties, and this will be one of the property which will be very much required when we have the convection diffusion system or the discretized convection diffusion system. Now, the another important is the boundedness of the profile. Okay. So, this has something to do with the first property of conservation. So, conservation only itself does not guarantee the boundedness. So, the conservation itself does not guarantee this boundedness. Okay. So, that means when I discretize the partial differential equations and the discretized equations, they need to be bounded. Okay. If you recall, for a element C we have written that AC phi C plus summation of F NBC AF phi F equals to BC. So, this discretized system also need to be bounded. If it is not bounded, because when we arrive this discretized system from the PDEs, that through the volume integral and surface integral, and we come down to this algebraic system, this is conserved. All your conservative properties in your PDEs and the properties in your discretized system, they are all conserved, but they do not guarantee the boundedness. So, to have the boundedness, you must have a criteria like minima of n phi F I must be less than phi C, maximum I to n phi F I. So, F I represents the ith neighbor of C and n is their number. So, essentially if you have a element like this and you have all the neighbor 1, 2, 3, 4, 5. So, there would be certain boundedness which are associated with this particular this thing. So, these are the important things that is essentially need to be satisfied by your discretized equation. So, that means when I come down from my PDE to a discretized system, I must fulfill those properties. From the discretized system, essentially I will get by linear system. Okay. So, that is what you get, and when you convert this PDE to discretized system, this is where you apply your numerical technique like FVM or FDM and get this system. Now, there will be couple of variable arrangements. One can, let us say for example, what we have chosen, I can have a geometry like this, and inside that I can distribute them in this kind of triangular element. Okay. Now, one option is that how do you basically this is called the arrangement. How do you store your variables? Okay. So, that will dictate a lot. Now, in this particular arrangement, one can wish to store his variable like at the cell centered. So, one can store the variable at cell centered. So, in that case it will be called cell centered arrangement. That means, whatever variable that we will be solving for, they will be stored at the cell center. And so far whatever we have discussed keeping the values at the cell center only. Now, one may, that means when I look at the cell center, so I have a particular element like that over which I will get the integration of my equations and get it. So, this is called the cell center arrangement. Now, one may wish to store at these points, at the vertex points. So, if you wish to store at the vertex point, this would be vertex centered arrangement. Okay. So, there are two different approaches one can adopt. One is the cell center arrangement, another is the vertex center arrangement. Now, accordingly, if you devise your finite volume scheme, then this will be called vertex center FVM, this will be called vertex centered FVM, and the other one could be called the cell centered FVM. Now, if you see the difference, so far we have only discretized our PDEs considering a finite cell and got a discretized equation. Now, while doing that, we did not bother to think about where to store the data or where to store the variable. Now, we slowly moving towards that. While doing the discretization, you need to have this arrangement. And why are they important? Because my physical problem, if you think about a flow through a channel, okay, my physical problem needs to be transformed to a computational grid. Okay. So, there when I transform my physical problem to this computational domain, I need to look at the arrangement of my variables, whether it would be cell center or at the vertex center, and accordingly my discretization process need to be taken care of. So, when I apply this process, before that this arrangement is very important. But what are the typical pros and cons with this kind of arrangement? Let us first look at this vertex centered FVM. So, what you do? You have this particular arrangement. So, here you store the data at these points, the vertex points, and if you have the centroid then they would be connected like that. Okay. Now, what it is essentially the one of the biggest disadvantage of this vertex center arrangement is that it is actually get you a lower order accurate method. So, the vertex centered system or the finite volume actually gets you back the lower order accurate method. And why? Because in this case the variables or the variables point values, because the variables represent point values, okay, and variation through the element can be computed using shape function or interpolation profiles. Okay. But this actually gets you a lower order accurate system, but one very good advantage of this vertex centered arrangement is that this allows or permits, it permits an accurate resolution of phase fluxes. Since the values are stored at the vertex center, so that allows you to permits to get an accurate resolution of the phase fluxes. But that is not only the advantage, apart from that these are having lot of other shortcomings, like if you think about in programming, the storage requirement is quite large, that means your data structure. So, you have to think about your programming point of view also, your data structure is quite large. So, the requirement would be large, that means you require high memory. Second problem is that if you have if you think about this particular phase and let us say you have specified a boundary condition here phi b, then the treatment of the boundary condition is not trivial. See, the other case, when you have specified a value, it was much easier to compute when you have stored things at the cell center. So, this would be another cons of this vertex centered, and also along with that you may have some more complications, like when you have complicated geometries with, let us say, complex geometry with sharp edges or cuts. So, if you have that kind of situation, then this vertex center arrangement is not very healthy. Overall, if you look at this particular arrangement, it does not give you too much of cost effective algorithm compared to the other one. Now, if you look at the cell centered, compared to the vertex center. So, similarly, if you look at your arrangements, so here the arrangement would be completely different. Here you store at the cell center. So, values are stored at the cell center. Okay. So, you have storage requirement is less. So, essentially the handling of data structure is easier, because only thing you need to know the connectivity amongst the neighboring cells. Okay. Also this gets you back second order accurate scheme. So, in general the cell center algorithm actually get you the second order accurate scheme. So, that is a good advantage of these things. But obviously, it does not come with all sort of advantages, some disadvantages are also associated with that. One of the very prominent one was that essentially treatment of non conjunctional elements. So, that becomes a problem. Also, the discretization of diffusion term in non-orthogonal system. Okay. So, as we move along, we will see when at least when we in the next lecture we will discuss about the mesh, we will see when the system is not non-orthogonal, that means the orthogonality is not there, then how difficult or not trivial would be the discretization of these terms. Okay. Another thing is that obviously there is a dependency of the result, dependency of results on grid. So, that means the order of accuracy is also dependent on the grid spacing. So, if you have finer grid resolution, so then, but this particular issue of the non-orthogonality issue of the diffusion term could be an biggest bottleneck. And for example, if you let us say you have a element, you consider one element like that, and you have a cell center C, you come to a face, so you goes like that E, from here you goes to F, this is N, this is T, and DCF distance, this is theta. Okay. So, this is the neighboring cell F, this is your SF. Okay. So, typically the discretization term of the diffusion term would be del F dot S. So, del phi dot E plus del phi dot T. So, this is essentially the implicit orthogonal like correction. Okay. And this particular term is the explicit orthogonal like correction. So, if you see that now if the theta that increases, the contribution of this term would be more. Okay. So, in that case this discretization will not or may not remain the remain is more robust. So, the robustness, so this is a situation when the non-orthogonality will come, non-orthogonal grid or the system, this will become. So, the only situation where the performance of the vertex centered FBM will be superior over the cell centered on some sort of a distorted grid. That is the only situation where you may have some superiority over cell center arrangement. Otherwise, in general the cell center arrangement is widely preferred and has lot of advantage, but obviously it does not come really free of cost. It comes with some disadvantages like non-orthogonality, discretizations of the diffusion term and all this that we will see later on, and how that can be handled easily. Now, apart from that, you have the implicit, this already we have declared implicit and explicit methods. So, this is essentially associated with the transient discretization. Okay. Discretization. So, the solution algorithm, the transient algorithm will have that dependency. Now, inherently what is important here is that the mesh support, okay, and that we will discuss in the next lecture. Thank you.